my table of contents. So I'm going to explain what do you mean by a braid group. So we also have the singular braid monoid, SMN. I go through some literature review for these structures, for representations for these structures. Then I'm going to introduce what is the aim of the article, then the two results that I have, and some suggested works. So first of all, in order to define the braid group, I'm going to introduce what do you mean by a braid. So a braid here, for example, just for simplicity, this is a braid of NB4. So we mean by BN, we mean N strings. So we have 4 strings as we are in B4, and each string is connected to a unique point from bottom and unique point from the top, in a way that we have over and under crossings. So the set of all equivalence classes of such braid are called it's called the braid group, and it forms a group. So as we can see here now, algebraically, the braid group Bn is actually a group that is generated by n-1 elements, which we call sigma 1, sigma 2, sigma n-1, and these are the shapes of these elements. We have these relations between these elements: sigma I plus 1, sigma I equals sigma I plus 1, sigma I plus 1, and we have commutativity or far commutativity whenever I minus j greater than or equal to 2. So in sigma I, we have overcrossing between ith and I plus 1th strand, while in sigma I inverse, we have undercrossing. So this is introduced in 1925 by Emil Artin. Another algebraic structure that we want to talk about, which extends the braid group, called the singular braid monoid, which is introduced in 1992. This is actually a monoid. So it's not every element in this group, in this algebraic structure is invertible. So we have SMN as an extension of Bn. Actually, we have the set of generators sigma 1 up to sigma n minus 1, the same of Bn, which are also invertible, but we have another family of generators which are non-invertible. We call tau 1, tau 2, tau n minus 1, and these are the set of relations between these generators. This is the shape of the generator tau I. So this generator is not invertible. That's why it's a monoid. Now let's go through representations of these algebraic structures. What do you mean by a representation? What do you mean by we're going to represent this group or this monoid? We mean that we give for each element in this group a matrix. So we represent each element in G, for example, if it's a group, by a matrix which is invertible, since every element in G is invertible. Similarly, for a monoid, we represent each element by a matrix which is not necessarily invertible, since not every element in the monoid is invertible. Why representation theory? Why it's important? For example, we use representation theory to solve many problems which are complicated. Actually, when you are going to represent each element in a group or a monoid by a matrix, we know how to deal with matrices more than dealing with complicated elements which are, for example, infinite group or infinite monoid. So one of the most important problems called the word problem. The word problem in group theory, if you have, for example, a group or a monoid, you have 2 elements which are, for example, huge. How can we distinguish whether these 2 elements are equal or not under some relations? So you can't know if the words are very complicated. A representation theory, if you have, for example, if we can define a faithful representation, a one-to-one representation, so we go from the word of groups to the word of matrices. So now, to distinguish whether 2 elements are different or not, we just know or just want to study their matrices. And studying matrices is very easier than studying complicated. So to prove, for example, 2 matrices are different, we just prove that the determinant is different, the rank is different, the trace is different, eigenvalues, and so on. So representation theory helps in solving the word problem in group theory. This is one of the applications. Of course, there are a lot of applications. For example, in knot theory, every braid is a closure, can be transferred to a knot, and so on. So now I'm going to describe the local representation. A representation is said to be local if it has this form. So it has identity above, identity below matrices, and here we have a block matrix. So when we say it's K local, this matrix is a block of order K. So it could be 2 by 2, 3 by 3, and so on. This is, for example, one of the most important representations, which is called Bureau representation, one of the most famous representations of braid group. This is 2 local. Since we have here a matrix which is 2 by 2, this is the standard representations. These representations actually we will need in our work. I'm going to introduce the aim later. So just this why I'm going to give their forms now. So this is Bureau, which is 2 local. This is the standard representation, which is 2 local, and this is the F representations, which is 3 local. So 3 local representation. Here T actually is indeterminate, so in Z of T plus minus 1. I am going to searching for braid group. Actually, we know a lot of representations of the braid group. For the singular braid monoid, since it's introduced in 1992, so we don't have a lot of representations of this monoid. So I'm going to extend the known representation as the singular braid monoid is an extension of the braid group. I am going to extend known representation of the braid group to the singular braid monoid. So in a way that one of the types of extensions is called local extension. So I'm going to give the form. We know that it's local representation. So the braid group, each generator sigma I has a block for matrices. So I'm going to give each tau I here also a block for matrices. But the matrix here is an I, not mi. So it's another matrix. Another type of extensions introduced by Bardakov, Spili, and Kozlovskaya, they prove that if we have a representation of sigma of braid group, we can extend a representation in this way. So each tau I will give this form. So we have now 2 types of extension. So you know that it's a problem. It's a problem to discuss. And how many ways can we extend? What are the extensions? Now the aim of the article. This is the aim. Can we find a relation between these 2 types of extensions? So if I have a representation of the braid group, I want to extend this representation to singular braid monoid. Can I have a relation between the types of extensions? So I have here 2 types. I considered in my work 2 types of representation. So so that's why I'm going to introduce in my work. I did this work in 3 representations that I said: Bureau, Rho B, Rho as the standard representation, and the F representation, Rho F. So I presented 3 representations which are known, and I'm going to study the relation of the extensions. So let's go through the results. The first result is that if this the Bureau representation, the extension of the Bureau representation is actually of any local extension. I said that we have 2 types of extensions: local extensions and phi type extensions. It has been proven that any local extension has the phi type. This is the phi type form. So actually, in Bureau representation, any local extension is a phi type extension. So this is not a big deal. I'm going to search now another representations where we can distinguish between these 2 types of extensions. So that's why I proved that for the standard representations, standard representation rho S, if T is not 1, its extension, local extension, is of type phi, is phi type. While if T equals 1, then rho hat S is of phi type if and only if Y equal O minus W. This means that there are some extensions that are local extensions, but not phi type extensions. So actually we have 2 types of extension which are different. So not every local extension is a phi type extension. Now moving through the The F representation, actually, it's like the bureau representation. Actually, I consider the F representation, since it's a 3 by 3 representation, 3 local. I just want to study in a variety. So the F representation, every local extension of F representation of the Brady group to the singular braid monoid is actually a phi-type extension. So the result where we distinguish between these two types of extensions is actually just for the standard representation. Now, the second result, I actually studied the faithfulness of these representations. So the faithfulness, what we mean, as I said, it's one of the reason why I study faithfulness is to study where the problem of this group or this monoid. Actually, I proved a necessary sufficient condition for the faithfulness of a representation, the extension of the bureau representation to SMN, but in the case n equals 2, so it's still an open problem for n greater than or equal to 3. Also, I find necessary and sufficient condition for extension of rho hat S, for extension of rho S, which is rho hat S, the standard representation to the singular braid monoid for the case n equals 2. Also, this is the necessary and sufficient condition. I'm going to describe actually the future work, which is very important. Till now, still we have the main question. I answered this question for these 3 representations, but we didn't answer it for general case. Can we find if rho is a k-local representation? I'm going to extend rho in the 2 ways, the k-local extension and the phi-type extension way. Can we find a relation between these 2 extensions for any cases? So this is a question. Another question, which is still new question. What are the forms of k-local representations? So we said that a representation to be k-local if we have shapes or the forms of representations of any group or any algebraic structure, monoid group, and so on. So this is also a question. Can we find another? We know till now these 2 types of extension. We know the k-local extension and phi-type extension from Brady group Bn to singular braid monoid SMN. Can we find a new type of extension, or just these are the extensions? And another question, which is answered 2 years or 1 year ago by Indian mathematicians, Dr. Madeti, I think. Can we generalize the concept of phi-type extension to another algebraic structure? They answered this question for the singular twisted virtual braid monoid, I think. So these are the questions, or these are the future work that we can. These are still an open problem that we can work on them, and these are the references. And thank you so much. I'm ready for any question.
Thank you very much. Are there any questions? Okay, then thank you very much.
Thank you. Thank you.
Thank you, Professor Hassan.
Okay. If you could please try to limit yourself to like 7 or 8 minutes, so we can finish until 5:30. That would be awesome.
Okay, the next paper is Olfat al-Lakis, Lawrence Fakih, Andrei Halanayan, Paul Georgescu, Stability Analysis in a mutualist model with 2 discrete delays. Please.
Good afternoon.
Hello.
Hello, good afternoon.
Good afternoon.
My name is Olfat al-Lakis, and today, inshallah, I will present this work in collaboration with Lawrence Fakih, Paul Georgescu, and Andrea Halanai. So now I will start. Today I will discuss the stability of mutualism model with discrete delays and how these delays influence species dynamics. So first, I will start briefly talking about first about the introduction. I will start with the motivation and then about the modeling context, introduce the delayed mutualism model, examine analytic stability results, explore non-linear stability scenarios, and then about the MATLAB simulation, after that conclusion and the future work, and finally the references. Okay. So let's start first with the motivation. Mutualistic interaction are essential in ecology, yet classical models even ignore delays that naturally occur in biological and process. This delay may significantly alter system stability. So our objective is to analyze their impact on the coexistence equilibrium. Okay. Now, the context and modeling framework. Here, I provide the broader ecological and mathematical context. As we know that mutualism involves both positive and negative feedbacks. So several modeling approaches exist, but delays are especially important because they are trigger oscillations or multi-instability, so multi-stability. So our contribution, our work introduced two discrete delay differential equation into an unknown mutualism model. So delivers delay dependent stability criteria and Hop thresholds and combines theory with MATLAB simulations to map the dynamics. In this slide, I introduced the system of delay differential equations with the two delays, tau 1 and tau 2. I explained the meaning first of the terms in these two equations. We have the growth, we have the mutualistic benefits, we have the delayed self-regulation, and how delays enter the system biologically. Now, in this slide, we will talk about the local stability without delays. So we took the three cases. The first case, it was about when tau 1 and tau 2 equals to 0. So as we can see that when tau 1 and tau 2 equals to 0, the system reduces to a classical ordinary differential equation mutualism model. So this gives us a baseline for comparison once delays are introduced. In the second case, the single delay Hop bifurcation. So we consider that tau 2 equals to 0 and that tau 1 vary where tau 1 greater than 0. So introducing a single delay changes the characteristic equation by setting eigenvalues to be purely imaginary. So instead of lambda, we replace I omega and we identify a critical delay where a Hop bifurcation occurs and oscillations appear. The third case, it was about two delays and stability regions. So what did in this case, when tau 1 is greater than 0 and tau 2 greater than 0, but tau 2 vary where tau 1 fixed. So when we have two delays, the system becomes richer, stability boundaries appear in the delay plane, and separating stable, unstable, and oscillatory regions. So what we did numerical computations confirms these boundaries. Three perturbation regimes around the E star. So even when linear analysis predicts stability, nonlinear responses differ depending on perturbation size. So we observe repulsion for teeny perturbations, attraction for moderate ones, and diverge towards another attractor for larger perturbations. So this is the case one, as I told you at the beginning of my presentation, that we said that tau1 equals to 0, tau2 equals to 0, and this is our baseline reference without delays. The system has stable coexistence equilibrium, and all trajectories converge to it. So this forms of the foundation for studying delay effects. In case 2, when the stability with a single delay, when tau2 equals to 0 and tau1 greater than 0, so we have one delay where tau2 equals to 0 and tau1 very greater than 0, so we will have one delay. So stability depends on what? It will depend on the sign of the key of coefficients. So if certain conditions hold, the system remains stable. Otherwise, we will have a Hopf bifurcation. So by MATLAB and simulation, we did MATLAB and simulation to illustrate this transition. In case 3, stability with 2 delays, tau1 very greater than tau2 very greater than 0, where tau1 greater than 0, but it is fixed. So with 2 delays, Hopf branches emergence, and we define thresholds for oscillations. So the smallest critical delays mark transitions from stability to periodic behavior. After that, we did the MATLAB numerical simulations to compare the 3 perturbation regimes for this very small for tau1, tau2 equals to 0, for moderate, and for large. These simulations visually confirm the theoretical predictions and highlight nonlinear effects. So simulation setting in tau1 and tau2 plane. In this slide, as you can see, that tau1 and tau2, we select 0.6, 0.7. Why? Because it lies inside the stable region. We tried for different tau1, different tau2, and we noticed that when tau1 and tau2 is less than 0.6 and 0.7, the system will not be stable, and greater than 0.6 and 0.7, the system will not be stable. So this slides explain why we select 0.6 and 0.7, because as I told you, it lies inside the stable region, but close to the Hopf bifurcation boundary, making it ideal for observing the 3 non-linear regimes. As a conclusion, I will summarize key findings: delay-dependent stability conditions, the emergence of Hopf bifurcation, and the 3 distinct non-linear responses. Delay significantly shape the system's behavior, as we talked about this part. And finally, our future work will include studying bases of attraction, constructing global bifurcation diagrams, extending the model to more species. And for sure, in order to, for this paper, we used different references. This slide or these slides list the scientific foundations behind the work, covering both mutualism theory and delay differential equations. Thank you for your attention. Any questions?
Thank you. There is any questions? No? Okay, thank you very much.
Thank you.
We will
Have a nice day. Thank you.
Thank you. We'll continue with our next
And
talk.
good luck for others. Yes.
Please try to keep it under 8 minutes. Our next presenter is Gezar Mohamed Amin with the paper Control with Minimum Energy Problem for Singular Two-Dimensional Continuous Discrete Linear Systems.
Can I speak?
Yes, please.
Doctor?
You have the floor.
Hello everyone. I am Kamal Benito, the second author and the corresponding author of the presentation of our professor Ghazal Amin. Until now, he is not available because he have or has emergency meeting with our ministry and our presidents because he is the director of our schools. Because of this, can I present her presentation behalf on Professor Ghazal? And secondly, I will present my presentation, if it's possible, of course.
So you want to present a novel approach to solving conformable fractional 2D state space continuous time linear systems?
And this is the second presentation. If I can, I will present the presentation of Professor Ghazal because he is not available. And I am a second author of, there is a mistake in the program because in this website and platform of university,
Okay.
we have made an inscription of Professor Ghazal and Professor Jilali Bouakada and Kamal Benito as a corresponding author. There is a short problem in the program.
Okay.
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 I can present?
Yes, sure.
Yes.
Yeah.
Okay. I make share. You see the presentation? Can I begin? Start? Thank you, sir. But I'm Associate Professor Kamal Benito from the University Abdelhamid Ibn Badis of Mustagana. I will present this presentation behalf on my professor Mohammed Amin Ghazar. For some reason, he has emergency meeting with our presidents and ministers. Donc, my first presentation is a minimum energy control problem for a singular class, certain class of two-dimensional continuous discrete time linear system, or we can call it the hybrid or mixed system. Well, I will begin by a short introduction of control theory and dynamical systems. Then I will give some preliminary results or some needed tools on numerical algebra and dynamical system to solve our problem. Our main result consists of two categories. The first part is controllability result using the Gramian matrix and the Gramian definition and the Gramian matrix, of course, associated our system. And then we conclude a new condition about how to calculate the minimum energy control problem for this class of systems. But the goal of this paper is to propose a new contribution to the controllability and the minimum energy control problem for a difficult or hard class of dynamical system, which is a singular two-dimensional linear system. The concept of controllability has a variety of application in advanced control theory and system research, as well as industrial and chemical reaction process, system and filter, 2D image processing and feedback, and 2D design technique. Many researchers have studied and developed this technique, and our technique is based, as I say, is based on two basic idea. The first, we must introduce the new definition about the controllability result using the Gramian matrix, and then we propose a new approach based on the Gramian technique to solve the problem of controllability and how we calculate the minimum value of the performance index associated of this system. Bon, let us consider our class of systems, which is described by the first equation. Note that E is a singular matrix, A is the state matrix, XTI is the variable of our dynamical system, B is the control matrix, and the UTI is the control or the command of our system. T, in this case, represent the continuous time variable, and Y is the discrete time variable. Well, first, of course, we must introduce the concept of controllability in the case of two-dimensional systems or the two-dimensional spaces. More precisely, for a hybrid case. Then the system one is controlled on the segment line, this line, with the t is greater than 0 and less than t final, and also y. If there exists a new control or a control uty or a command which transfer or steer the state of our system from the initial cases to the final state. Note that the final state we can denote it, or we can represent it by these subs. Our technique is based on Kronecker Weierstrass decomposition. And for this, we must assume that E is not an invertible matrix, and it means the determinant of the pencil Ez minus 1 is different to 0 for some z in C. If this condition hold, then we can say there exists two invertible matrix P and F according to this decomposition. This decomposition is called the Kronecker-Weierstrass decomposition. Its idea is to decompose the singular system, this singular system, because it's complicated, to a new equivalent subsystem. The first state is denoted by system 5, and second is by subsystem 6. If we can derive conditions of controllability and minimum energy control problem for these two subsystems, then we can easily say that the first general and hard system is controllable, and then we can calculate the minimum value of the performance index. We can begin by studying this class of system and then this class of system. Note that the energy diffused by the first system is the total or the sum energy diffused by these two subsystems for subsystem 5 and subsystem 6. The solution of this subsystem 5 is given by the following formula. It's a classical solution for a standard system and classical system. And X1F type and B1 bar are denoted by the formula 8 and 9. We can use Laplace transform or Sumud transform and Z transform to calculate this solution. The U bar, the control vector, is denoted by the formula 10. First, we present our theorem, our main theorem. The subsystem 5 is controllable on the segment line TF0, TFQ, if and only if the following Q1 is a non-singular matrix. It means it's a invertible matrix. Why we must assume that it's a non-singular or invertible matrix? Because in the minimum energy control problem, we must use the inverse of this matrix. So if this matrix is invertible or non-singular, then the subsystem 5 is controllable. And moving to the second subsystem 6, which is the formula is which the solution formula of subsystem 6 is given by X2F type. And then we must conclude a new it's our contribution to calculate the Gramian matrix associated to the second subsystem. The subsystem 6 is controlled on segment line TF0, TFQ if and only if the following matrix Q2 is non-singular. And this is the new definition and our main result in this presentation. Not done, B2 bar is denoted by this matrix, and G the transpose is a non-potent matrix, so we can calculate easily these sums. And finally, we can conclude by using the existing result about decomposition and chronicle decomposition of our singular matrix. The system 1 is controlled on the segment line TF0, TFQ if and only if the two matrices Q1 and Q2 are non-singular. It means to ensure the controllability of the first subsystem, we can use the controllability of the two extract or the two obtained subsystems. The second part of this contribution is called minimum energy control problem. The minimum energy control problem is a good is a good result, and it helps us to calculate the minimum value of this performance index because this performance index is represent the energy and level of energy diffused by a general or any dynamical system. Note that in this formula, this quadratic formula, Q1 is a symmetric definite matrix. We can express or formulate our problem to the following subsystem. I will use the idea of the sum of energy diffused by the system 5 and subsystem 6. To solve this problem, we must assume that we have two invertible matrix Q1 and Q2. And to solve this problem also, we define the following matrix W1P, which represent matrix, Gramian matrix, to ensure the controllability of the first subsystem. And also, and in this case, we present our powerful tool, a new control vector, which is described by the formula 5. This formula used the inverse of the Q1 matrix and also the new this matrix, the inverse of this new matrix. For this reason, we have assumed that these two matrices or the Gramian matrix associated are our subsystem are invertible, to allow us or to help us to calculate the optimal vector or the optimal command. And if we use this formula to in this formula 13, we can conclude that the minimum value or the optimal value of our performance index is given by formula 16. Donc, this is for the second, for the first subsystem 5. And in equivalent tools, equivalent result, we can deduce the new formula. Not that this formula is a new form or a new equation in control theory. This the performance index associated to the second subsystem 6. To solve out the problem of minimum energy control problem, we must introduce a new Gramian matrix associated to the second subsystem 6, which is represented by the formula or the expression 18. And finally, this also before the final result, I will present the optimal vector, which give us the minimum value of the minimum energy diffused by the subsystem 6. It's given by the equation 19. And the minimum value then, finally, the minimum value of the second subsystem is given by the following theorem. And the final result, we can...
to interrupt you, could you please wrap it up?
What?
You
time?
can hurry up with your presentation, please.
Yes, yes. I will move to the final examples and our examples. It's look at that singular system, and we want to ensure the controllability and calculate the minimum energy control problem of our systems. And using some simulation and MATLAB results, we can see effectively that the minimum value with the new control vector is less than that any other input vector which ensure the controllability of our system. Donc this graph, this figure one, illustrate and confirm the applicability of the applicability of our techniques and methods. And here's some bibliography and related papers and books mainly are given by Professor Tatsuka Sorak and some other scientific research. And thank you for your attention.
Thank you very much.
Thank
Are there
you.
any questions? Okay. I ask of you to please keep your presentations to under
Yes.
8 minutes. So
Yes.
we can
Yes.
go through all of the presentations. We have a short amount of time allotted for us.
Okay. Excuse me for the time.
It's okay. I'm sorry for interrupting you, but
It's okay. I will present it rapidly.
okay. So my colleague will introduce you in the paper.
The next paper is Kamel Dinetu, Vijla Bugada,
Bugada.
Yazar Mohamed Amin, a novel approach to solving comfortable fractional 2D state space continuous time linear systems. Please.
Yes.
Okay.
I will present my second participation, which is called a novel approach to solving conformal fractional 2D space models, considering the continuous times model, of course. Donc, I will present it rapidly, which is I will give an abstract, introduction part, some preliminary results, and then I will give the general solution of the first form of Fornazini and Marchesini models, and the second form of this Glasgow model. And I will conclude this part by some numerical results and conclusion. Donc, we can present in this paper the interest of a new class of fractional derivative, which is called the conformable derivatives. This derivative is presented in the last 10 years by Professor Khalil and Professor Abdjawad in the last years. This fractional derivative is more easily than Caputo or Emmanuel to use it in a practical problem for testing positivity or stability or controllability result in a dynamical system. For this reason, I will present some mathematical background of this fractional derivative. This fractional derivative is expressed by the first equation and the first definition in the class of one-dimensional model, of course. Some properties of this derivative and integral fractional conformal integral derivative. Not that this result exists in literature, but our main idea is to extend this formula to the case of two-dimensional conditional models. For this reason, we present a new fractional derivative, a new double integral in this case for two functional variables xt1, xt2. T1 and T2 are a continuous variable, and x is the state variable of our dynamical systems. It is complicated comparing with the first cases, of course. In our definition, we introduce, it's my contribution, it's a new derivative in the case of two-dimensional system, which is will describe dynamics on two directional directions. It's mean for example, for horizontal and vertical axis in the case of a plan, of course. For this reason, we introduce a 2D fractional Marchesinian models, which is described by the expression tan. For this reason, also, we must introduce Laplace transform in the case of two-dimensional variables. And some needed results, some new results to calculate, of course, the solution. Because in the first case, I will use the conformable double Laplace transform to calculate the solution of this model. For this reason, we must introduce this lemma, the first equation and second properties to calculate this solution. And we present also the convolution theorem in the case of our fractional derivative. It's expressed by the following theorem and the following formula expression. Using the previous result, the convolution products and this lemma, we can easily conclude that the solution of our system or state space equation is given by the following theorem or the equation 16. Note that the phi is or represent the state matrix or the transition matrix according to our systems. We can calculate this matrix using the following formula by we can deduce this formula also using the characteristic polynomial and comparing the coefficient of P and S in the case of two-dimensional model, of course. For a second class of model, I will present and introduce a new class of systems. This is the second for this code is the second form of Farnesian and Marchesinian models. While A1, A2 are the state matrix, B1 and B2 are the state or the control matrix, and this value WT1, WT2 is the control vector, and T alpha, beta, T1, T2 is represent the second or the fractional derivative of this variable xt1, xt2 according to two directions, T1 and T2. We introduce some needed definition to give the solution of our problem. Not thus in this part we use a new transform which is called the double sum-modulo transform. Before this definition, I will present a new definition or a new set of function. This new set of function ensure us existence and the convergence of the sum-modulo transform to allow us to help us to calculate this transform for the state space matrix. This sum-modulo transform, this conformal sum-modulo transform, is given by this following equation. Note that we can see there is a duality relationship between sum-modulo transform and Laplace transform. We present in this part some simulation as some result of this transformation to also to calculate the second solution with the use of a different approach. This is the next one, the next result. And the third result is a lemma to calculate the sum-modulo transform of this specific function to calculate the final solution. Using this result and also this theorem, we can conclude that the solution of our second system is more complicated than the first class of models, which is represented by double sum series and finite series. Actually, in numerical analysis, we can make a limit of this this double sum because this transition matrix uh, for example when we have big value of E and G, this matrix is are equal 0. Donc, so this solution is also converge and exist in many cases, of course. For simple cases, we make a numerical simulation of these papers. We consider the 2D linear systems with some value alpha and beta, and the state space matrix A0, A1, A2, and the enforced system. The input of our system is it's academic example also heavy side distribution. The solution of the state space equation for a zero boundary condition is given by the following formula using the first solution, of course. Using a simple example, and note that phi minus 1 minus 2 is equal 0 for many cases, for g is greater than 2. So we can conclude a simple formula, xt1, xt2 is given by the following vector solution, and we can easily do the simulation of these vectors by MATLAB and using command plot and fplot command. The solution is given by the following figure: x1 to the first component of x1, x1, t1, t2. As a conclusion, we have derived in this case two main results. We have first extend the general fractional derivative in the case of two-dimensional system. We have used Laplace transform to solve this solution, to solve the solution of the first form of Fornazini-Marchesini models, which is the systems are very, very, very difficult to calculate because it's not easy to apply Laplace transform and then inverse transform to obtain the result. And second part, we have developed a new model transform in the case of two-dimensional system. Of course, we use conformal derivative in the case of two-dimensional system, and also we have present some numerical example. It's an academic example, I told so to test our result and to test the applicability of the proposed approach. And excuse me for also, it is my bibliography which I used to calculate or to realize this part of work.
Okay.
Thank you. Thank you very much.
Thank you. There are any questions?
No? Then thank you again.
Thank you, Professor.
Our next talk will be given by Bogdan Maxim, who will talk about a doubly nonlinear parabolic problem with variable exponents, homogeneous Newman conditions, and generalized logistic source.
Thank you very much for the introduction. I will start and be as rapid as possible. Can you hear me? It's okay?
Yes.
I start with this problem. So we have two nonlinearities. One nonlinearity is B, and the other one is in the flux operator. I consider Neumann boundary condition on that problem, and it has many applications in image processing. This is where I'm interested to use this kind of things. I work with variable exponents, so my intention is to denoise an image. So the second one is the image with noise, and using this kind of techniques with variable exponents, I can remove the noise, but maintaining the edges of the image. So the variable exponents will help me to do this. So it's kind of Laplacian, but with a P Laplacian, but with a variable exponent. These are the variable exponent spaces in which we work, the Lebesgue and Sobolev spaces. These are their properties. They're a little bit more complicated than the constant ones. Some of the hypotheses I use, in a Lipschitz domain we work, I drop the condition of the source to be locally Lipschitz. These are some necessary hypotheses in order to have a convergent scheme to my problem. The main idea, I will skip some things, is the definition of the solution. I work with weak solutions, and I'll try to solve this kind of problem. You see, if V equals U, then the two terms with B cancel, and we have a solution to our initial problem. The first step is to show that this problem has a solution. The second step is to show that this operator that connects U and V has a unique fixed point. And lastly, that the solution converges to a steady state. To obtain this kind of results, we need a parabolic comparison principle. This is not so hard to deduce. I put a complete proof here, but there's no time for it. The operator S that connects V and U exhibits these three properties. It is monotone, continuous, and has exactly one fixed point. To obtain the fixed point, we use some monotone methods. We obtain a minimal solution and a maximal solution, and then we show that the two are equal. So no other solution can be. To deal with double nonlinear parabolic problem, we need to discretize the derivative, the time derivative, and making this difference cotangent here makes us work with an elliptic problem, which is simpler to deal with. This was done by me in a previous article, and I used the results from there to solve this elliptic problem. This will generate a scheme, and the Vm and tilde Vm. This will approximate my solution as m goes to infinity, but there are a lot of calculations. I only stated here the steps in which the conclusion is attained. I'll skip this part too. A lot of theorems are to be used here, Alaoglu, Eberlein-Smulian, Lebesgue-dominated convergence, Soban-Simon, a lot of classical theorems from functional analysis. Having this proved, or the proof works with an regular initial data. In order to work for an irregular initial data, we need to make an approximation of the initial data with more regular data and apply the results obtained. But this will drop a little the regularity. We will lose some regularity of the solution. So we have here a h1 function if the initial data is regular, and after, if it is not regular, we have a local Sobolev space here. Okay, in some cases, the steady states can be proved to be unique. This is a theorem from a previous article. And if the steady state is unique, then the solution to the double nonlinear problem converges to the steady state as t goes to infinity, but the convergence is only in L2. I succeed proving it only in L2. So this kind of results apply to some kind of problems like the multiple phase problem, with multiple Laplacians here with variable exponents. The theory goes well for them. Here we have 0 and 1 because we deal with images by modulating them with functions, with values, intensity values between 0 and 1. So 0 will mean black and 1 will mean white. And the grays are in between. Some future directions of research. I want to study the regularity of the steady states, the regularity of the solution, and try to obtain a strong maximum principle for the doubly nonlinear parabolic problem, and then to generalize all the ideas for reaction diffusion systems with double nonlinearity. This is my bibliography, and thank you very much for the attention.
Thank you very much. Are there any questions? No? Then thank you again for your presentation.
Thank you.
Okay. The next paper is Mahmoud Ibrahim, Global Dynamics of a Tumor Growth Model with Three Mechanisms. Mahmoud Ibrahim is online with us. Okay.
Okay, he doesn't appear to be online. Then our next talk will be given by Kisi Mohamed El Amin, Abdelkader Nakmek, Andrei Halanay, Mohamed Bouziem, and Mohamed Helal, and it is entitled Understanding Xylella fastidiosa Spread in Olive Trees Through Delayed Differential Modeling.
Hello everyone.
Hello?
Hello. To my presentation.
No.
2 seconds.
Not yet.
Now?
Yes.
Okay. So, dear Professor, distinguished chair, session moderator, and esteemed colleague, good afternoon. I am Kisi Mohamed El Amin, doctoral student at the University of Jibril of Sidi Bel Abbas, Algeria. And I am pleased to present our research entitled Understanding Xylella fastidiosa Spread in Olive Tree Through Delayed Differential Modeling, which is conducted in collaboration with my supervisor, Abdelkader Nakmek, and Professor Halanay, Professor Ainsbach, Professor Bouziem, and Professor Mohamed Helal. Before starting our presentation, let's take a look of my table of content. We start with a small introduction. After that, we will see the study of our model. So the introduction is about the biological phenomenon. What is Xylella fastidiosa? Xylella fastidiosa is a gram-negative bacterium that can cause disease in a wide range of plants, including grapevines, citrus, and other plants, and particularly olive trees. This bacterium is considered a major threat to forestry and agricultural industries worldwide, as it can cause significant economic losses. This bacterium is transmitted by an insect such as a sharpshooter and spittlebugs. Once inside the plants, the bacterium colonizes the xylem vessel, which are responsible for transporting water and nutrients throughout the plants. So we are interested to studying a hybrid mathematical model that describes the dynamic of this Xylella fastidiosa. To facilitate our analysis, we first assume that we have not the vertical transmission. So we have only the dynamics between the susceptible and infected olive trees. After that, we will simplify this model to obtain a reduced delayed formulation, which allows for a deeper understanding of this bacterium. So in our model, we consider a population of olive trees, otherwise in good health. Our variable are S of t, size of sensitive olive trees, I of t, infected olive trees. We have the variable A here denotes the age of the disease, which means it means that the time that has elapsed since the infection olive trees became infected. We also introduce lambda, the density of new olive trees, mu as the mortality rate of all healthy olive trees, mu I the mortality rate of olive trees with the Xylella fastidiosa, V0 here the rate of the removal of infected olive trees, and we note that I equals the integral of I of TA is the total population of infected olive trees. So our model is the following. The first equation of susceptible olive trees is an ordinary differential equation, and the second one is a partial differential equation that modelize the infected olive trees. After that, we assume that here mu I of A is a constant positive. The probability of infection is equals to 1, and I of TA equals to 0. So after, by using the characteristic in the first model, it can be written as a delayed formula as shown here. The term of delays appears here. So we assume that I of 0, the initial condition of the age-structured model shown in the first diapo, is continuous on 0 till. And this phi1 can be taken as a constant S0 in C minus tau 0 R plus square. And this phi2 can be taken as I0 minus T exponential minus mu I plus V0 T. Let's move on to the existence of equilibrium points. We see that we have two equilibrium points. The first one, when we don't have the infection, I star equals 0, we get the disease-free equilibrium. And the second one, the endemic equilibrium, when we have I star positive. We know that I star must be positive, so the endemic equilibrium exists if and only if lambda is greater than this term. So let's define R0 of tau is this formula, and this R0 of tau can be seen as the basic reproduction rate. For the local stability of equilibrium points using linearization of the system, we get the characteristic equation corresponding to the equilibrium S star I star is given by this equation. So for the first equilibrium, which is the disease-free equilibrium, we see that if we put I star equals 0, this term is equals to 0. This term also equals 0. So the first eigenvalue is lambda equals minus mu s, which is negative. But the second term is depending to exponential minus lambda. So using the theorem or the method of Cookes and Grossman, we only need the sign of this eigenvalue. So we prove that if R0 of tau, when he is less than 1, all the eigenvalues are negative. And if it is greater than 1, there exists an eigenvalue with a positive real part. So if this R0 of tau is less than 1, the disease-free equilibrium is locally asymptotically stable. And if it is not, the disease-free equilibrium is unstable. We also prove that the endemic equilibrium, when it exists, but the same way of Cookes and Grossman, if it is greater than 1, the endemic equilibrium is locally asymptotically stable. Then we proved the global stability of the disease-free equilibrium by using a Lyapunov-Grozovsky functional, and we proved that if it is less than 1, he is globally asymptotically stable in the invariant set n between 0 and lambda over mu s, and it is globally unstable if it is greater than 1. Let's finish by some numerical simulation by using a parameter shown here in this table and the program MATLAB. The first scenario, when R0 of tau is equal to 0.7, which means less than 1, and tau, the delay equals to 37, we shown that the healthy olive trees tend to lambda over mu s, which is 100. And also the infected olive trees is a decreasing function to 0 here, which is the disease-free equilibrium. The second scenario, it is when X0 of tau equals 1.2, greater than 1, and tau equals 34. We observe that the healthy olive trees tend to the endemic equilibrium, S star equals 82, and the infected olive trees also tend to the endemic equilibrium, I star equals 10, which is which the both scenarios are agree with our theorems. In conclusion, our study began with the formulation with an H2 model, and we simplified this model to a delayed model. We studied the existence, the stability, the local stability, the global stability of the disease-free equilibrium, and we illustrated our theorem by different cases in MATLAB. Our perspective are, well, so we are going to try to introduce the vertical transmission, which means we will have an equation of 4 compartments: sensitive and affected olive trees, and sensitive and affected vectors, which mean the sharpshooter or the spittlebox. We will approve our work by numerical simulation and a study of this model. And after that, we will try to introduce different control to our model to try to reduce the spread of this bacterium, Xylella fastidiosa. Here are some references used in our work. I would like to make acknowledgement. This work was supported by the 2025 Eugene UNESCO Scholarship, founded by the Romanian Ministry of Foreign Affairs in collaboration with the Agence Universitaire de la Francophonie, IUF. I would like to thank and acknowledge the National University of Science, because I was there for its academic support and research facilities. So thank you for your attention.
Thank you very much. Are there any questions?
Yes, I have one.
Yes, please.
Yeah.
From practical point of view, what's the unit you are using for theta, for the delay? So you are using years or what other?
I didn't hear you. The delay tau?
Yeah, in which unit you are counting the time?
The unit, it's years.
Years. Okay.
Yeah.
And do you observe also some correlation in between that time and I saw that it's giving a delay, a horizontal delay of transmission. So it's in any way closer to what you observe for any value, specific value of theta. So you are having, or you are having just few test values for, I don't know if I'm expressing myself sufficiently clear for.
So, here in this research, we just make some value of the delay.
So just test value, nothing test. Yeah. Nothing compared with the way in which it transmits, the bacterium transmits to the olive.
Yeah, basically the transmission of this bacterium is from there are some insects that transport this bacterium. But here, to facilitate first our analysis, we neglect the vectorial transmission. So we propose the H structure glue, and after that we reduce it to the delay model, the delayed formula, and by using two 2 or 3 value of this term, we approach our analysis to the real phenomenon.
But you don't have yet a definite value for theta. That's what I meant. The final one.
Maybe I forget it.
Just a test.
Yeah, maybe I forget it.
Okay, thank you.
Thank you very much. Thank you.
Okay, the next article is presented by Mansuria Saidini, analysis of solutions for higher order linear difference equations with finite phi order coefficients. Mansuria Saidini is online.
You do not have your microphone on. Can you turn on your mic? Okay.
Yes?
Okay.
Did you hear me?
We can hear you now.
Yeah, okay. Do you see my presentation?
Yes.
Yes.
Okay. So, hello, everyone. I'm very happy to be with you today to present some of my research entitled Analysis of Solutions for Higher Order Linear Difference Equation with Finite Few Order Coefficient. In this talk, I will start by a brief introduction, giving some motivation results, and I will present the main results and some lemma used to prove in this work, and I will conclude with a conclusion and a brief list of references used in our studies. The objective of this work is to study the graph of solution to higher non-homogeneous linear differential equation of the form 1, where the coefficients I, G are entire or monomorphic function. We obtain some new results on the phi order of solutions to such equation. So, Novana theory is a branch of complex analysis that deal with the study of monomorphic function. It was introduced by Rolf Novalina. It provides a way to measure their growth using the Novalina characteristic function, and that's the reason why this theory has become an important tool in the study of differential and difference equations. So the first part of this representation is devoted to the necessary definitions and notation of Novalina. At first, we remained the definition of containing function by two following integrals. The first one is for the zeros of monomorphic function, and the second one for the poles of the monomorphic function. We define also the proximity function of a monomorphic function by the two following formula. Now we can define the characteristic function of a monomorphic function as the sum of the proximity function f and the containing function of f. And as an example for f equals exponential of alpha z, where alpha is a no-zero real number, we have the characteristic function of f is alpha r divided by p. We can introduce now the concept of the order of monomorphic or order of growth of monomorphic function of f by the limit of the logarithmic of the characteristic function of f divided by logarithmic of a. And in this talk, also we use the definition of the lower order of a monomorphic function by the first limit and of an entire function by the second limit. We also need to do following definition of the convergence of exponents of the zeros sequence of the poles sequence of monomorphic function. And to root this work, we assume that phi is a no decreasing unbounded function, satisfies the two following conditions. And we can now define the phi order of the phi order of normal function by the following lemma limit, and the lower phi order of f by the limit f of logarithmic of the characteristic function divided by log of r, phi of r. As an example, if we take f of z equals z squared divided by 4 and phi of r equals logarithmic of r, in this case we obtain the phi order of f equals 1. We have also the definition of the phi convergence exponent of the pole sequences of f defined by limit strip of logarithmic n r f divided by logarithmic phi of r. We need also the following definition about the phi tip of f and phi lower tip of f, where f is a homomorphic function. And the difference of alpha of f in this case for I different to infinity and I is infinite number. So in the recent years, several authors have investigated the growth of solutions of second order and higher order of order homogeneous and no homogeneous linear difference equation with entire or meromorphic function. Recently, Belaidi and Belama made some previous results of Liu and Zhang by generalization their results from homogeneous difference equation to no homogeneous difference equation of the form 2. By they supposed that all coefficients of the equations are entire function, and they supposed also that there exist two arbitrary leading coefficients AL and AK. That have the same lower order and different lower tip, and they suppose that maximal of tip of all coefficients AG is less than the lower tip of AL. So they proved that every meromorphic function solution f has an order of growth greater than the lower order of the leading coefficient AL. In the case when all coefficients of the equation 2 are meromorphic, they under the same conditions as above, they supposed also that the convergence exponents of poles of AL is bounded by its lower order. In this case, they proved that if the second member of the equation is different to 0, that means that the equation is no homogeneous, then they obtained that every solution f of this equation has an order of growth greater than or equals to the lower order of the leading coefficient AL. And if the equation 2 is homogeneous, in this case, the order of the solution is greater than the lower order of the leading coefficient IL plus 1. So there is an interesting question. Can we obtain similar results to the previous one by considering the phi order instead of the order of growth of the coefficients? The main aim in this work is to answer this question by improving on the results of the work mentioned above. So the following theorem represents our first result concerning the no homogeneous linear difference equation 2 with entire coefficient. In this result or in this theorem, we suppose that all coefficients of the equation are entire, and we suppose also that there are two arbitrary leading coefficients AL and IK that have the same lower order and the same lower phi order and the different lower phi tip. And we suppose also that the phi tip of all coefficients Ig is less than the lower phi tip of Al. In this case, we obtain that every meromorphic solution F of this equations has an phi order of growth greater than the lower phi order of leading coefficient Al. In the following theorem, we obtain a result concerning no homogeneous linear differential equation, but with meromorphic coefficient. So under the same condition as above, we also suppose that the leading that the convergence, the phi convergence exponent of pole of the leading coefficient Il is bounded by its lower phi order. In this case, we can obtain two results. If the second member of the equation 2 is different to 0, so that means that the equation is not homogeneous. In this case, we can prove that every solution F of equation has a phi order of growth greater than or equals to the phi lower order of the leading coefficient Al. But if the equation is homogeneous, so that F, the second member, is equal 0, in this case, the phi order of the solution must be greater than the lower phi order of Al plus 1. I will briefly present the main outline of proof of our result. So firstly, by writing equation 3 as follows, and using the following lemma of Goldberg, and our lemma with the Bengetat and Belaidi, and the following lemma, we can obtain the result. In a similar way of the proof of theorem 1, we can write the equation 2 as follow, and we use the following lemma, the previous lemma and the following lemma of Gunderson and data. We can obtain the result. So as a conclusion, toward this work, by using a generalization concept of phi order, we have discussed the possibility of extending some results about the growth of meromorphic solution of linear difference equation of the form 4 and 5, where H, G are no zero distinct complex number, and the coefficients are entire or meromorphic function. We have obtained the relationship between the solutions and the meromorphic coefficients in terms of phi order and phi lower order. I will conclude this talk with a list of some references used in this work. Thank you for your attention.
Okay, thank you. There is any questions?
I have just a small remark about the title writing in the program.
Okay.
Yes, the title of my presentation is analysis, not is that analysis?
Analysis.
Okay,
It,
analysis.
yes, it means an A.
Yeah, well, we noticed that
After
there are some letters missing.
Yes, thank you very much.
Thank you.
Thank you.
Have a nice day.
Thank
Have a nice
you.
day. Thank you.
Our next talk will be given by Mohamed Najib Ben Ammar, Mohamed Amin Gezar, and Tilali Bouagata on the topic on the controllability of positive fractional 2D continuous time linear systems. Is Mohamed Najib Ben Ammar or Chilali Bogada present. Mohamed Amin Kezar. Okay. We will come back to them there.
Okay, the next paper is presented by Marilena Ciontescu, the variational approach to optimal control with generalized environment convex interval valued functionals.
Hello, I'm here. One moment.
Thank you. Is everything okay?
One moment, I cannot upload. One moment.
Okay. Please hurry up. Is everything okay? Hello? Marina Chantescu? It's okay?
Is everything okay? Do you need help with anything? Do you need more time? We can move on to the next talk and then come back to you.
Okay, it's better to be the next. Then I will to be the next, please, because I don't know what happened. Sorry for this.
Okay. It's okay. It's okay.
Okay, thank you.
Then our next talk will be given by Mario Salin Dragu on the topic on a tumoral growth model with constrained curvilinear integral functionals and gradient type variations.
Yes.
Okay, we can see your presentation.
Can you see my presentation?
Yes.
Okay. Hello everyone, my name is Marius Alendragu and today I'm going to present my study entitled on a tumor growth model with constrained curvilinear integral functional and gradient type variations. This presentation will be divided into 4 parts. First, I will present the research background. Next, I will run through the optimization of a curvilinear integral functional with gradient type variations. I will specify that we highlight the theoretical findings by
real-life application, for example, tumor growth model. And finally, conclusions. Optimization problems are widely used in engineering, in classification, in mechanics, or in medical engineering. For example, brain electrical activity can be seen as an optimization problem via Maxwell equations. The accuracy of the design model is influenced by the proposed architecture, so that in numerous cases, the computational results cannot include all details about the original problem. To overcome this limitation, we extend the functional optimization theory, introducing gradient type variations. In this way, the aim of this paper is the optimization of constrained curvilinear integral type functional by considering gradient type variations. The main findings highlight the non-homogeneous Euler-Lagrange type partial differential equations and illustrative biomedical application. Next, we'll talk about the optimization of a constrained curvilinear integral function with gradient type variations. First, we define the mathematical ingredients. For example, omega, small omega, represent the m-dimensional dependent variable. If omega is associated with time, we say that we have a multi-time problem. H is the state function having n components, is a map from capital omega to Rn, and H gamma is the first order partial derivative of H with respect to omega gamma. We consider the complete integrable Lagrange one form of C2 class, G nu, which depends on H gamma, and omega. I would specify that I will use in this study Einstein summation, which means summation after repetitive indices. In this case, omega subscript, nu subscript, nu superscript. This one form can be extended as G1 d omega 1 plus G2 d omega 2 plus Gm d omega m. Before to define the problem, we introduce gamma being an arbitrary piecewise differentiable curve linking the endpoints. Now, having all ingredients, we assume there exists a Lagrangian G such that the total derivative of G with respect to omega nu is G nu. We should find a M-sheet function H star that minimizes the path independent curvilinear integral functional I defining on gamma curve and containing G nu Lagrangian between all C2 class functions satisfying boundary conditions and partial differential equation constraints by considering gradient type variations, as I said at the beginning of this presentation. To solve this problem, we apply the Lagrange multiplier theory. In this way, we consider the Lagrange multiplier P is a vector function which helps us to create a new Lagrangian composed from the old Lagrangian, and the product of Lagrange multiplier components and partial differential equation constraints. This strategy helps us to change the first constrained optimization problem into unconstrained one. In this case, we have the new Lagrangian composed from the H function, H gamma, omega, and the Lagrange multiplier P. As I said at the beginning of this presentation, we established the necessary conditions of optimality for feasible solution. In this way, we are this theorem if H star and P star minimizes the previous problem, and this one form represents a pullback for another one form, there we have this system of partial differential equation for H and P. Compared to classical variation, in this case, we obtain non-homogeneous Euler-Lagrange partial differential equation. We have a constant in the right hand side, we not have equal to 0, creating a novel perspective, innovative perspective in this field of calculus. As an application for this theory, we consider a dynamical model for tumor growth, which starts with the following question: how should a cancer cell optimally allocate available resources between metabolism and growth for a given therapy to have a significant effect? To address this problem, we consider a two-dimensional dynamical system that describes the temporal evolution of the effects of tumor growth. So we have two times, omega 1 and omega 2. Omega 1 is associated with observer time, and omega 2 is associated with intrinsic time. And the function k of omega representing carrying capacity, a dynamical variable proportional to the amount of neurovascularization. The tumoral tissue is supposed to have a large number of cells, so that the neurovascularization is the primary factor in governing the available resources, the oxygen and nutrients. L of omega, tumor cell population, and T of omega representing chemotherapy treatment concentration, T1 in the central compartment in the blood, and T2 in the tumoral tissue. To formulate this problem, we apply a pipeline inspired from economical problems in which the core is to introduce the production function and denote H, the state function, as the ratio of carrying capacity to L of omega, to tumor cell population. After repetitive steps, we are led to the first order Lagrangian, which determines the following curvilinear integral type cost functional. Applying the given theorem, we obtain the solution. Next, we will speak about the simulation results. The scope of the aim of this simulation is to numerically describe the evolution of chemotherapeutic agent in central compartment, as you can see in the first figure, and in the peripheral compartment, as you can see in the second figure. Analyzing these heat maps, we can observe different ranges of values. For T1, we have the maximum of 40 arbitrary units, and for T2, we have a maximum of 1.5 arbitrary units. More importantly, these heat maps highlight distinct shifts in dynamic patterns along omega 1. For T1, we can observe a pronounced decrease, and along omega 1 for T2, we can observe a pronounced increase. Along omega 2, both T1 and T2 show a consistent downtrend, indicating a continuing reduction in concentration. This pattern may be related to the metabolic elimination process of a chemotherapeutic agent. However, previous studies have considered single time model, which limit the validity of this interpretation. In this figure 2, we have the numerical results for the H, which is the state function, H of omega 1 and omega 2. One can see the treatment effect. Once the concentration of chemotherapeutic drugs start to increase, the tumoral tissue H start to decrease. The drug action can explain the phenomenon. Higher intratumoral dosage enhances the destruction of cancer cell neovascularization, resulting in tumor cell death. Finally, conclusions and further research direction, we have established the necessary optimality condition for constrained model involving multidimensional Lagrangian partial differential equation constraints. The proposed framework, formulated in accordance with the considered class of perturbed function governed by gradient type variation, highlighted the right-hand controlled while a Lagrange system, and perspective, for example, biomedical signals can be modeled as optimal control problem. Fetal electrocardiography or the inverse problem of electroencephalography represents a milestone in applying the foregoing theory, considering Maxwell equation and considering control function and state function. Thank you for attention.
Thank you very much. Are there any questions? No? Then thank you very much again.
Thank you.
Marilena Ciorchescu, it's there.
Oh, yes, I'm here. I will try again. Sorry.
Okay.
It's okay?
Yes?
Yes, it's okay. You may start the presentation.
Yes. Okay, thank you very much, and sorry again. So, my name is Marilena Ciorchescu. You already repeat my name 2 times, and I'm from National University of Science and Technology, Polytechnica Bucharest, Romania. and I will present a study, a variational approach to optimal control with generalized invariant convex interval valued functionals. So, in this study, some generalization of the convexity notion and their application to optimization and control theory have been established. We investigate the solution for a class of optimal control problems under interval-valued generalized convexity assumption for the involved functionals. What we have here, we have a functional K defined on Cartesian product between Rn and Rp with the value is in I, when I is the family of real interval values bounded and closed. And we have a smooth state function x defined on interval a to b including reals with values in Rn, and then piecewise continuous control function u defined on the same interval but with values in Rp. The interval valued functional k formulate as what is written here. We say is the interval valued continuous differentiable and functional if it satisfies the condition KL is less than or equal to KU. We notate with X the space of piecewise smooth state function, and also we notate with U the space of piecewise continuous control function occupied with uniform norm, both of them. Now we formulate and we study and investigate the primal optimization problem driven by an interval valued const functional. This problem we notate with P and represent minimum of these pairs X, U belong to the set of state function and control function, and this problem subject of three constraints. The first one is inequality, the second one is equality, and the third one is boundary condition, where K is a functional C1 class interval valued functional, and KL and KU defined like this are real with the same domain and codomain like our functional K, but with codomain reals. And F and G sub J are differentiable interval valued for F, and differentiable real valued function is J sub G. We consider, we denote omega the set of feasible solution of P, and what we have is a definition, what means L optimal solution of our problem P. And we continue, and we present the Karush-Kuhn-Tucker type necessary optimality conditions association with our problem P. And these conditions are presented in theorem number 1. And we continue with sufficient optimality condition under convexity and under pseudo-convexity and quasi-convexity. The first theorem sound like this. What we have a feasible solution X star U star, and the constraint function satisfies the suitable Tucker constraint qualification in this point, and the relation 1, 2, 3 from theorem above are satisfied. And more, we have some functional under absorption of convexity. If this inequality is satisfied, then we can say that this feasible solution for our problem P become an LU optimal solution to our problem P. And the second theorem is similar with this, but is under absorption on pseudo-convexity and quasi-convexity. So we have a feasible solution for our problem. The same, the constraint function satisfying the suitable Tucker constraint qualification in this point. The relation 1 to 3 from theorem are satisfied, and the next function are sub-assumption of first pseudo-inversity and the other quasi-inversity. And if this inequality is satisfied, we can say this is become an LU optimal solution for our problem P. So in this paper, we introduced this control function, and we established several generalizations of the notion of inversity and explore their application in optimization and control theory. So we investigate solution to a class of optimal control problems under interval value generalized inversity assumptions for the associative functional. The study stop here, but my work is in progress, and sorry, I am not on video. I continue the study with duality, and what I have in plan, and also I started to formulate the dual problem, and after to find relationship between our problem and primal problem and this dual problem. Thank you for your attention.
Thank you very much.
Okay, thank you. Is there any questions? Okay.
Thank you again, and sorry for all this to the left, to the right. Thank you.
It's okay. The next paper is presented by Sowad Salmi, Jilali Bogada, a new perspective on the LML region and D&D stability of fractional multidimensional state space models.
Yes, I'm here.
Okay. So you can start.
Are you seeing my presentation? Are you seeing my presentation, please? Good morning, all. My name is Selmi Suad, and I'm a doctor in Faculty of Exact Science and Computer Science, University of Abdelhamid Ibn Badis of Mostaganem. It's my pleasure to present to you our research entitled A New Perspective on the LME Region and Data Stability for Fractional Multidimensional State Space Models. This work was conducted under the supervision and the guidance of Professor Jilali Bouakada and represents the core finding of my research within the ACS team Laboratory of Pure and Applied Mathematics. As many of you know, fractional order systems have attracted significant attention in recent years due to their unique ability to model complex real-world phenomena with inherent memory and non-local effect features that classical integer order models. Studying the stability of fractional multidimensional systems that change in several spatial directions, is difficult, especially when there are uncertainties or what? Yes, I present my introduction. Studying the stability of fractional multidimensional state space systems that change in several spatial directions is difficult, especially when there are uncertainties or external disturbance. These systems appear in advanced applications such as signal processing, control, and geospatial modeling. In this presentation, I will propose a new LMEs-based method and extended in the idea of data stability region to fractional multidimensional state space models, offering a clear way to guarantee their robust stability.
To give you a clear roadmap of this presentation, I will now outline our main objectives. First, I will define the spatial research problem we are addressing. Second, I will present the precise mathematical formulation of this problem. Then I will introduce our novel approach using LME region and data stability analysis. This will be followed by numerical examples, and finally I will conclude some key reference. Let us start with the core research problem. The objective of this presentation is to analyze the fractional multidimensional state space systems. In particular, we investigate the stability region of a new class of a fractional linear multidimensional state space models, and we provide tractable conditions based on linear matrix inequalities. Now that we have identified the research problem, let me formalize it mathematically. Our problem formulation consists of two key parts: the open loop system and the closed loop system. First, we consider the generalized formulation of the generalized fractional Roser model, the open loop system, where ED, which assumed invertible, AD is the dynamic matrix, B, C, and D are the control and the output and the transmission matrix respectively. XD represent the state of sub vectors. And the KD of power alpha 1 to alpha D represent the matrix of differential operator diag SE of a power alpha I multiplied by the matrix identity of order NE in the Laplace transform when the system 1 in the continuous time, or diag ZE of a power alpha I multiplied by the matrix identity of order NI when the system 1 in the discrete time. U and Y represent the input and the output vectors respectively. The closed loop system. Assume that the realization or the system 1 is minimal and strictly stable, which means that all generalized eigenvalue in the set gamma I in the complex plane, where I vary to 1 to D. If we close the loop with U equal to delta Y, we obtain the perturbed system given by this equation, and A to delta obtained by this formulation. We now arrive at here to our contribution, a new framework for guaranteeing robust stability using LME region for fractional multidimensional systems. Our main results provide compatible conditions to ensure the system remains stable within a desired region of the complex plane, even when subject to perturbation. First, we define what constitutes LME region for multidimensional system. Region D in the complex plane is an LME region if there exists a symmetric matrix Li and Mi obtained by this formulation. Definition. So inspired by the reference 3, the fractional open loop system 1 is stable in the region D if and only if all poles in the region D, but this definition is not directly applicable. Our first main results provide necessary and sufficient conditions for the stability of the open loop system. So in this theorem, we represent the condition for the open loop system is stable in the region D. Theorem 1, the fractional open loop DD system is DD stable if there exists a symmetric positive definite matrix Y such that the LME4 is satisfied, where theta E equal to P over 2 multiplied by 1 minus alpha I.
Let's now suppose that the fractional open loop DD system 1 is stable in the region D, and we for the sufficient condition to guarantee that the closed loop system 2 is also strictly stable. For the perturbed closed loop system, our second main result establish a sufficient condition for robust DD stability theorem. The closed loop system 2 remained stable in the region D for all perturbation delta, where norm 2 of delta is less than strictly 2 gamma of a power minus 1. If there exists a matrix Y and P positive, definite positive, such that the LME5 is satisfied, where Q1 and Q2 obtained by the singular value decomposition of the matrix Diag ME, where E vary to 1, 2, D. Examples. To validate our theoretical development, we now present a numerical example that demonstrates the effectiveness of our LME-based approach. We consider a 2D continuous time fractional system with the following parameters: ED, A, B, C, and D, and alpha 1, alpha 2, the fractional order. We define our stability region using the following LME parameters. This particular choice defines a specific sector region in the complex plane. By solving the LME condition from theorem 1, we obtain a feasible solution confirming open loop system is stable in the region D, given as below Y1 and Y2. Furthermore, applying theorem 2 gives us the robustness margin gamma. Hence, we can conclude that the closed loop system 2 is also strictly stable. Some references are available in the published paper. And thank you for your attention, and I welcome any question you may have.
Okay, thank you very much.
Thank you.
Are there any questions? No? Okay, thank you again.
Merci. Thank you.
Thank you.
Next talk will be given by Stefan Van Anton on the topic fractional parameter fusion for CNN model version merging.
Yeah, sure. Can you see it?
Yes?
Okay, thanks. Can anybody hear me
Yes?
correctly? Okay, thanks. So, as you said, fractional parameter fusion. My name is Stefan Van Anton. I'm a PhD student at Faculty of Applied Sciences. I study applied physics, trying to do combining AI with microscopy methods. I'm also a member of this center, Professor Thomas Center. The main motivation for what I try to do today to show you is the fact that ensembling or weight averaging is a known method that works. You can read this paper about it. So they show that it works, but what they showed it has some limitations. The first limitation is averaging across a single run, right? Where I have a model, I train it for a number of epochs, and then I choose the best one. The problem is that I lose the rest of the epochs. Basically, it's not wasted compute, but it's near it. So from 100 epochs, let's say I just choose the first one, the best one, and I lose 99 epochs. I might want a method that combines some of the epochs, so I gain some more accuracy. For example, you can do that by exponential moving average across the last epochs, and you gain some improvement, a better generalization. Another method is averaging across multiple runs. As you'll see, usually you vary your hyperparameters and you choose the best one again, but the rest of them are wasted.
This paper shows that you can do fusion with different hyperparameters, but only if the models lie in roughly the same loss basin. So if they converge to the same space in weight space, basically. So my idea was, instead of simple averaging, just treat each parameter evolution across epochs as a time series and apply fractional calculus, and maybe you get rid of these two problems. This is basically the main figure for my text. The work is usually, you have the starting point, the amount of hyperparameters, you train the model, right? And you choose the best one. And then you vary the hyperparameters and you choose the best one from this matrix. You can see that they converge roughly to the same area. So if I choose the best one out of these, I just wasted the compute for all the others. So why not try this naive averaging, what is tried before, and I gain a little bit more of accuracy. But I can also try what I'm proposing, the fractional fusion, and I gain like 2% more accuracy for free. I don't need to train anything again. I just combine the parameters. By the way, this is the starting point. And here is the zoom in version. So you can see that this difference is basically free accuracy that you gain simply by applying one step of fractional calculus. The naive way to do it in a single epoch, a single run, is exponential moving average, where you have your lambda here. This is only for 2 models, but it can be extrapolated to any number of models. You have your lambda, you choose your lambda, whatever you want it to be between 0 and 1, and whichever works best, you select that. And suddenly you have a model which is better than all of the models during your epochs, and this helps you with the generalization. But the weakness is that you introduce an exponential bias, so it focuses on the last epoch, basically. Again, wasted compute in the earlier epochs, and you ignore the shape of the training trajectory. This is very important because you leave some accuracy on the table. Okay. My approach is basically using fractional calculus in this whole procedure. With your training sequence, starting from the first epoch to the last epoch t, you treat it as a discrete signal, you apply the Gruen-Lendikov fractional integration, which is just the normal formula, but instead you stick here the gamma function instead of a factorial. It's very easy, and suddenly you gain a better way to do weight averaging, because you still get recent epochs that have higher weights, but now you gain earlier epochs that still contribute. So you're not wasting the early compute. And I have a figure that shows that you obtain a sputter representation of rather than naive averaging. Okay, this is the figure. You can see for the variation of lambda parameters and the alpha parameter in the fractional integration. I will zoom in on this region, the end flow. So from 19th epoch to the 100th epoch, basically every model that I've tried to do fractional calculus on is better at the end than the naive way of averaging. So for free, I can gain 1% in accuracy just by modifying the equation that I do the weight averaging on. But for a more complicated method, maybe I want to average multiple runs, so the high parameter runs. Another example, just for 2 models, again, it can be extrapolated to any number of models. I just do naive merging, again, 3 problems in this. Because of the scale differences in those 2 weights of the models, right, I get bad results in the early epochs. We will see in the figure. And if the trajectories differ slightly in the early training, actually I will get a bad overall results because they won't converge in the same loss basin. And it actually leaves some improvement on the table because I do not account for the trajectory. I do not account for the structure of the weight evolution. So even in the best case, when it works, I can still make it work better by introducing fractional calculus. And the way to do it is you compute the Gruen-Lendikov fractional derivative along the epochs. So basically this thing right here. This extracts your long-range correlations. It provides a smoother representation of the direction of movements, and it allows for a more robust merging space compared to just using the raw parameters. So that's what I'm doing. I'm just doing merging, but instead of doing it in the parameter space, I'm doing it in a fractional derivative space, which is sort of like working in the Fourier space. So simplifying your problem, with Fourier transform, doing some analysis or some computation and then reversing back. The same thing, but in fractional derivative space. This will emphasize my trends rather than the absolute parameter values, and it will provide more stable Bayesian preverbing behavior. After you do this, you just need to go back to the weight space by applying the inverse Grun-Analytikov operator, so basically the integral. The anchor point is the weight at epoch 0, because all of them at epoch 0 are the same, because they start from the same initial model, which is a pre-trained model. Apply this formula, and now you get the trajectory that stays close to the both original runs, while you preserve the Bayesian structure at the end, so you can do weight merging. Hey, this is basically, there's something in the chat. We can see the slides. Okay. You do naive merging, you get this, basically. So it jumps all over the place because they don't lie in the same loss basin. So one of the models is here, another one is here. If I do weight merging, they end up in the worst place. The next one, fractional bending, I can get rid of that by modifying this loss structure using fractional calculus, and you see it's a smoother representation, and it leads to a better loss, so it's a lower loss, so it will lead to higher accuracy. Again, I tried it with 3 models, 2 classicals, one ResNet and VGG, and a more complex one, PVT, which uses transformers. It has like 10 times the amount of parameters than these 2. Again, you can see that fractional blending is the best in all cases, rather than naive averaging. You get basically 1% improvement in the training run, and on the distribution shift, so you're testing, you get 2% improvement, so which proves that you get better generalization. Something interesting to say for the PVT model is that the difference between the naive averaging and the fractional blending is actually less than in the other cases. And that leads me to believe this disclaimer that no one can guarantee that it will scale to LLMs, for example, so on bigger networks, because of what I observed with the PVT. So maybe it's theoretically should work with any architecture and should improve it, but nobody can guarantee until you run it. So maybe somebody else can run it. But I've proven that in this case, specifically, fractional calculus provides a powerful dimension for posterior merging, basically makes merging better, and blending in derivative space is better for loss Bayesian stability. I've shown that there is not so much jumping around in the early epochs, and that reconstructed models have a smoother decision boundaries because I have the better accuracy. Okay, thank you. Don't forget this figure. And if you need to contact me, maybe you have some other ideas, you can use this email.
Thank you very much. Are there any questions? No? Okay. Thank you very much.
Thank you as well.
The next paper is presented by Abdelaziz Oualid. Boundary value problems for fractional differential inclusions with Caputo-Hadamard type derivatives.
Is Abdelaziz Oualid present? Okay, we will come back to her. Okay. If need to. We'll move on to the next presentation given by Nizrin Miliani, Jilali Bawagada, Kamel Benetou. Analytical methods for stabilizing fractional multidimensional discrete.
Yes, I'm here.
Okay, please.
Yes.
Okay, can you start the presentation?
Yes. Wait a minute. Can you start? Can you start my presentation?
Sorry?
Can you start my presentation?
You need to start the presentation on your own.
Yes.
I think you tried to share the screen
It
earlier.
was visible.
It was visible.
Yes, I have a problem. Wait minutes. Yes. Can you start? Yes. Good morning, everyone. Yes. My name is Nisreen Miliani, and I hold a PhD in mathematics. I obtained my doctorate from the University Abdelhamid Ben Badis of Mostaganem in Algeria. Today, I'm pleased to present my research on analytical methods for stabilizing fractional multidimensional discrete system. First, let's start by presenting the table of concepts. Next, I will present the introduction and the problem statement. In the following section, I will discuss the analysis of multidimensional discrete time linear fractional models. And the next part of this presentation is devoted to the stability test of multidimensional fractional system. And we finish it by the conclusion and bibliography. Now, the objective of this work are solvability problem of multidimensional fractional system Rosal type, and the second stabilization test developed using the gain matrix of fractional dimensional Rosal models. Now, in introduction, the multidimensional fractional system are mathematical models that describe phenomena evolving physically in several directions. These are therefore models in which the derivative operator is placed. And they are therefore models in which the derivative operator is replaced by a fractional operator. Multidimensional fractional system have been used to model various phenomena such as diffusion, wave propagation, fluid mechanics, and more. They are generally considered valid and reliable for modeling certain physical phenomena. However, it is important to note that there are limits to their use, and that is necessary to verify their validity of each specific application. The stabilization of multidimensional fractional dynamical system consists in ensuring that the system converges toward an equilibrium state of desired trajectory despite differences of variation in initial condition. To achieve this, different control approaches can be adopted, including tools based on the gain matrix. It's essential to take into account the system limits and specific conditions during stabilization in order to ensure optimal use. Now, we will begin by presenting some preliminary remarks and concepts The definition 1, the horizontal two-dimensional discrete function x in order of order alpha defined by the first formula, where alpha between n minus 1 and n. In definition 2, we define the vertical two-dimensional discrete function x of order beta, defined by formula 3. This lemma is correct for the breadth. We present the generalized definition for our model. This definition, the fractional difference of order alpha g of the multidimensional discrete function is defined by formula 6, where alpha g between n minus 1 and n. At the subsequent definition, we define it using this formula. And in the following, we introduce a general formulation of the fractional discrete time multidimensional described by the Russell model, given by this equation 1 and 2, where matrix A is the state matrix, X is the state vector, U is the control vector, and A, B, C are the matrix appropriate dimension. According to definition number 4, the system time can be rewritten as following, given by this equation number 11. Such that A bar given by this formula. And to achieve our objective, we define the Z transform in multidimensional in order to find the solution of our system, given by formula number 13, where X represents the Z domain or representation of the sun. With the scope of our object in extension of the Cayley-Hamilton theorem is considered for a multidimensional system. Using definition 5, we obtain the following results. And the polynomial characteristic on the characteristic polynomial of a Russell multidimensional system is defined by this equation, where NE in Z are determined by the number LE. Now we present our results. This theorem, the solution of the system number 10 is of the following form. With B defined by this vector, and all the T is the matrix, the transmission. Now we pass in definition the described fractional DD models is asymptotically stable if and only if the state X, the trajectory X, converges to 0 for a 0 input with all boundary initial conditions are all boundary conditions satisfying. Now we consider the system 11 with the following state feedback U, the new control, where U equal the K is the gain matrix, times X, the state vector. where K are in R, K is the gain matrix. And our models then become presented by this formulation after substituting the new control input state. This system is positive and acceptably stable if the result is satisfied in this theorem. The theorem, the fractional system 22 in closed loop is positive and acceptably stable if and only if there exists a block diagonal matrix phi defined by this formula number 2013. Satisfying this condition number 25 and the condition number 26. And the gain matrix is given by formula number 27. To obtain the stable gain matrix of a closed loop multi-dimensional fractional system, we present below the procedure to follow. 1. In the step 1, choose a block diagonal matrix 23 and a real matrix defined by formula 24 that satisfies condition 25 and 26. In the step 2, from condition 27, calculating the gain matrix K, the new matrix. Now we test the validity of the previous result. We consider our multidimensional fractional system. We start by example. We consider the multidimensional fractional system for D equal 2 and alpha 1, alpha 2 equals 0.6 and 0.7 with A given by this matrix, and found a gain matrix K such that the closed loop system is positive and asymptotically stable. Using our proceeding, we obtain the following in step 1. We choose the phi 1 and phi 2 satisfying the condition, and D1, D2, and we verify the condition precedent, where the conditions are satisfied, and in step 2, using the formula 27, the gain matrix is given by K equal this, given by this expression.
I'm sorry to interrupt. Could you please try to wrap it up?
Yes.
Okay, thank you.
Yes. And from the obtained matrix, the closed loop system is positive because 2 coefficient is positive. In this case, the characteristic polynomial can be written in the following form. And since all the coefficients are positive, the closed loop system is therefore asymptotically stable. In example 2, on the other hand, for the example, the fractional Rosel models with alpha, beta, and the matrix, new matrix, we use the proposed approach to confirm our result, and we then obtain by matrix K equals 0.0200 we given the closed loop system is asymptotically stable since all the coefficients of this characteristic polynomial are positive, and by the K equals 001, 008, the closed loop system is asymptotically stable because all the coefficients of this characteristic polynomial are positive. And here is the graphical representation of X with the horizontal and the vertical axis respectively. Now, finally, we concluded with the conclusion. In this study, we have presented the class of multidimensional fractional system. And to solve the solvability problem for this class of system, we use the Z transform and the development of a technique based of the gain matrix and the characteristic polynomial, which allowed use to establish necessary and sufficient stabilization condition for multidimensional fractional system. And we finish it by some reference. And thank you for attention.
Thank you very much. Are there any questions? Okay. Thank you very much again.
Thank you. The next paper is presented.
Thank you.
Okay. The next paper is presented by Ana Gabriela Tamaș, Mircea Șușcă, numerical methods for solving Sylvester and Lyapunov equations, challenges and implementation in MATLAB.
Yes.
Please proceed.
Sorry, just a second. Can I be the next, please? I have a problem right now. And I have to leave the meeting to enter again.
Okay.
Okay.
Thank you. Thank you.
Then we will move on to the next talk. If they are ready, Alina Claudia Precu, Mircea Șușcă, Vlad Mihai Mihali. They will give a talk on convex formulation of approximate feedback linearization and convergence rate control.
Yes, can you see my presentation?
Yes, please. Thank you.
Okay, good afternoon. I'm Alina Prekov, and today I'll be presenting the work carried out with my co-authors Mircea Șușcă and Vlad Mihali from the Technical University of Cluj-Napoca. The title of my talk is Convex Formulation of Approximate Feedback Linearization and Convergence Rate Control. Here is the outline of the presentation. I'll start with a short introduction and the main motivation. Then I'll review the necessary tools we use in this work. After that, I'll present the proposed method. Then I'll show a case study on the classical ball and beam system, and I'll finish with a brief conclusion. First, let me give some context. Exact feedback linearization transforms a nonlinear system into an equivalent linear one through a suitable change of coordinates and an appropriate input transformation. This works very well when certain conditions are satisfied, in particular when the system has a well-defined and constant relative degree. However, in many practical situations, this relative degree is not well-defined everywhere, for example, near singularities, and in those cases, exact feedback linearization cannot be applied. The objective of our work is to develop an approximate feedback linearization framework for such cases. We aim to preserve the local linear structure as much as possible while compensating for the remaining nonlinear terms. At the same time, we want to guarantee Lyapunov stability and be able to tune the convergence rate of the trajectories toward the equilibrium. Now I'll introduce the basic setting. We consider a set of first-order nonlinear equations written in one. We recall two classical notions. First, system one is feedback linearizable if these two conditions are satisfied. Second, the relative degree of the system, which describes how many times the output must be differentiated until the input appears explicitly. Under this assumption, we can construct a local diffeomorphism as shown in 2. In these new coordinates, the original nonlinear system is transformed into what is known as the normal form. The functions gamma of x and alpha of x define the corresponding input transformation. Here we can see the explicit normal form of sigma n. If we choose the input according to this expression, the nonlinear term in the last equation are cancelled out, and we obtain a linear system in the z coordinates. We then close the loop with a linear feedback V, where the matrix AC minus BCK is for bits. This is the classical exact feedback linearization framework. Next, I briefly recall the notion of control bearer functions, or CBF. We start by defining a safe set C. A function b of x is a control bearer function for system 1 if there exists a class K function delta, such that the inequality in 6 holds for all states. A simplified version of this safety condition is shown in 7. Intuitively, this means that the trajectories are pushed back into the safe set C. Now I move on to the proposed method. We consider the linearized system in normal from 8, which contains a residual nonlinear term num of z. If we neglect this residual term, we obtain the approximate model shown in 9. The eigenvalues of A tilde determine the exponential convergence rate toward the equilibrium point. The problem can be summarized as follows. The residual nonlinearities can become large near singularities, so we introduce an auxiliary input W that compensates num of z. The idea is to design W so that the system in 8 behaves as close as to the ideal model in 9. To design W, we first look at the autonomous version of the approximate model, where W equals 0. We consider the quadratic Lyapunov function and its derivative as shown in 11. When we include both the auxiliary input and the residual nonlinearity, the derivative of the Lyapunov function splits into 3 terms: Xc1, which comes from the nominal linear dynamics, Xc2, which depends on the auxiliary input W, and Xc3, which contains the residual nonlinearities. Our idea is to compute W by solving an optimization problem. We minimize the magnitude of W subject to a linear inequality that ensures the derivative of V remains negative. However, this optimization may become ill-posed when phi of z is close to 0, because in that case, the influence of W on V dot almost disappears. To avoid undefined or unbounded solutions, we must ensure that the cancellation condition shown in 14 is not satisfied. We encode this condition using the CBF type constraint shown in 15. The bear becomes active only when the state approaches that problematic region. The time derivative of B is computed also in 16. Using the expression of B dot from the previous slide, we obtain the inequality in 17. The inequality is linear in the variable W, and it can be written compactly as in 18. The final convex optimization problem is given here. The auxiliary input W is then computed as the solution of this convex optimization problem. To illustrate the method, we consider the classical ball and beam system. On the left, we see the mechanical setup and the equations of motion together with the corresponding input transformation. On the right, we have the state space model with state X, and the output is simply the ball position on the beam. We observe that if either X1 or X4 are 0, then gamma of X is 0, which means that the relative degree is not well defined. We now apply the coordinate transformation shown at the top of the slide. In these new coordinates, we obtain the normal form on the right, and the linearized dynamics can be written compactly as in 20. This is exactly the same structure we used earlier in the abstract derivation. For the numerical study, we select the eigenvalues of A tilde as listed here. This choice fixes the closed loop convergence rates and yields the feedback gain K shown in 21. We then solve the Lyapunov equation and we obtain the matrix P, which is used in the function V. Finally, we choose the initial state Z0, which places the system in a region where the residual nonlinearities are non-negligible. Also, these plots compare the uncompensated case where W equals 0 with the compensated case obtained from the convex optimization. On the left, we show the derivative of the Lyapunov function, and on the right, we show the state trajectories. Without compensation, V dot becomes positive for some time, which means that the design exponential stability is lost. With compensation, V dot remains negative, ensuring asymptotic convergence to the equilibrium point. Here we visualize the auxiliary input W and the three components of the derivative of V. The input W is active mainly during the transient phase when the residual nonlinearities are significant. The right plot shows that the compensation eliminates the positive contribution of C3 and keeps the total derivative negative, which corresponds to consistent energy dissipation in the Lyapunov sense. Let me conclude. We have proposed an approximate feedback linearization framework that can handle systems with an ill-defined relative degree. The resulting closed-loop system ensures local asymptotic stability and allows us to shape the convergence rate directly through the eigenvalues of that linear model. The ball and beam example shows improved stability properties and effective control of the convergence toward the equilibrium point. Well, thank you very much for your attention.
Thank you very much. Are there any questions? No? Okay, thank you again.
Thank you.
Thank you. So, Anna Gabriela Tomasz, are you
Yes, I'm back. Yes.
Okay.
Can you see my presentation?
Yes, it's okay.
Yes, can you hear me?
Yes.
It's okay?
Yes.
Okay, thank you. Hello everyone. My name is Ana Gabriela, and today I will present our paper called Numerical Methods for Solving Sylvester and Lyapunov Equations, Challenges and Implementations in MATLAB. Next. This is the outline of my presentation. I will start with the motivation, then I will talk about the mathematical background and the numerical methods we used. After that, I will show how we implemented them in MATLAB, present some results, and I will finish with the conclusions. Now let's talk about the motivation of our work. The Sylvester and Lyapunov equations are very important in control engineering. We use them to study how a system behaves and to design controllers. They are not easy to solve. That's why we need methods that are fast and stable to get good results. There are many methods available, but each one has different performance and stability. So, in our study, we compared several methods, all implemented and tested in MATLAB. Now, let's move on to the mathematical background of our paper. On this slide, we can see the two main equations we used. The first one is the Sylvester equation. It involves matrices A, B, C, and the unknown matrix X. The equation has a unique solution if the matrices A and B have no eigenvalues in common. The second one is the Lyapunov equation. It is a special case of Sylvester equation. It is used for stability analysis of linear systems. If the matrix P is positive definite, that then the system is asymptotically stable. Next, let's talk about the numerical methods we implemented in MATLAB. After understanding the equations, the next step is to see how we can solve them. One common approach is to use Schur decomposition. In this method, the matrices A and B are transformed into upper triangular forms, so the system becomes easier to solve. Schur decomposition can be done using different methods, like Gram-Schmidt orthogonalization, householder reflectors, or Givens rotations. On this slide, we can see the Gram-Schmidt orthogonalization method. The method is simple and easy to implement, and it takes the columns of a matrix A and turns them into orthogonal vectors one by one. When the matrix is not well conditioned, the Gram-Schmidt method is numerically unstable because it is sensitive to rounding errors. The next method we will talk about is Schur decomposition using householder reflectors. This method uses a special matrix called reflector, denoted with H, which helps to eliminate the elements below the diagonal. By applying several reflectors, we can turn the original matrix A into a upper triangular matrix T. The method is more stable than the Gram-Schmidt, and it's efficient for large matrices. Next, we will talk about the Schur decomposition using Givens rotation. A Givens rotation works on just two rows or two columns at a time, helping to eliminate one by one the elements below the diagonal. By applying a sequence of Givens rotation, we can transform the original matrix A into an upper triangular matrix T. The orthogonal matrix Q is obtained as a product of all the Givens rotation obtained before. Next, we will talk about the main steps of the MATLAB implementation. As you can see, there are on this slide we have the general forms of the matrices for the Sylvester and Lyapunov equations. The process includes 4 steps. First, we generate the matrices A, B, C, or Q. Then we solve the equation using different numerical methods like such as Gram-Schmidt, householder reflectors, or Givens rotations. Then we compute the residuals, which you can see on the slide. And finally, we compare all the obtained results in terms of numerical accuracy and stability. Next, I will talk about the results I obtained and some conclusions. As we can see from this table, from the results, the Schur decomposition using Gram-Schmidt orthogonalization produces the largest residuals and should be avoided, while the Schur decomposition using householder transformation is recommended because it produces more accurate results. That's all. Thank you for your attention.
Okay, thank you. Are there any questions? Okay, thank you very much. The next paper will be presented by Alvescu Ana, connections between exponential and polynomial concepts for random semi-dynamic systems.
Hello.
Hello.
Can you see the slide?
Yes, but it's
very small.
It's very small. It's in portrait mode. Can you? Okay.
Oh, it's okay.
Okay. I can't join the meeting from my laptop, so I will presenting using my phone.
It's okay.
My name is Oana Albescu. I am a PhD student. I'm at Transylvania University of Brașov. The title of my presentation is Connections between exponential and polynomial concepts for random semi-dynamical systems. Have a problem. Okay. It's okay? Okay. The presentation is structured as follows. First, I will discuss some preliminary results. Second, I will address exponential stability. Next, I will analyze polynomial stability, and finally, I will present the Lyapunov type characterizations. Now, let me introduce shortly the basic notation and the framework we will work. On the next slide, the application phi maps and definite linear random one-sided discrete time side on X over theta, which is a measurable semi-dynamical systems. Throughout the paper, we denote the system simply by theta phi r dts. On this slide, we give two important definitions for the system theta phi. First, the system is called non-uniformly exponential stable if there exists a theta invariant random variable alpha and the function n such that the norm of phi decays exponentially with rate alpha up to the factor n omega. Second definition, the system has non-uniformly exponential growth if there exists a theta invariant random variable xi and a function m such that the norm of phi grows at most exponentially with rate xi up to the factor m omega. In short, these definitions describe whether the system's behavior decays or grows exponentially in a non-uniform random way. The next slide. This theorem provides criterion for non-uniform exponential stability of a system that already has uniform exponential growth. It says that the system is non-uniformly exponential stable if and only if there exists a theta invariant random variable beta and two functions n and d such that the growth of the system can be controlled in a specific integral sense. Now we introduce Lyapunov functions, which are very useful tools to the study stability. You can think of a Lyapunov function as a way to measure the size of energy of the system state. The main idea of the theorem is this. Systems with uniformly exponential growth is non-uniformly exponential stable if there exists a Lyapunov function that degrees along the system's trajectory in a controlled way. Now let's talk about polynomial stability. In this case, the system still stabilizes over time, but more slowly than in the exponential case. The rate of decay depends on the system and can vary randomly. These propositions give equivalent ways to describe non-uniform polynomial stability. Essentially, all three statements describe to the same type of the decay behavior, just in slitting different form. Here, we defined non-uniformly polynomial growth. In this case, the system's state can grow over time like a positive power of t, depending on a random variable. In this proposition, give equivalent ways to describe non-uniform polynomial growth. All three statements equivalently shepherd the same growth behind in slightly different forms. This theorem says that such a system is non-uniformly polynomial stable if there exists a theta invariant random variable beta and two functions s and k such that the future behavior of the system can be controlled in a specific integral sense. The next theorem says that the system is non-uniformly polynomial stable if there exists a theta invariant random variable and functions s that also has to control the size on the system's state over time. Finally, we move to the Lyapunov approach for polynomial stability. Here, Lyapunov function is a tool that helps us measure the size of the system state in a Lyapunov sense. In first theorem says that a system is non-uniformly exponential stable if and only if a related system defined by think to logarithm of time is non-uniformly polynomial stable. The second theorem shows the reverse. A system is non-uniformly polynomial stable if and only if related system defined by think to exponential of time is non-uniformly exponentially stable. In conclusion, there is a strong connection between non-uniform exponential and polynomial stability. Finally, here is the list of reference I use for this work. Thank you.
Thank you very much. Is there any questions? Okay.
Thank you.
Thank you. Thank you. Our next talk will be given by Andreea Punțan. on the topic on the upper bound of the third Henkel determinant for the class of star-like functions of order A.
Can you start?
Sorry? Okay, you can start. We can see your presentation, but can you zoom in on the PDF?
Yes.
Okay. Okay, perfect.
You can start.
We cannot hear you if you're speaking.
Microfonul, Andreea.
Turn on your mic, please. We cannot see your screen. Okay. But we still cannot hear you.
It's okay?
Okay,
Now
we can hear you.
We can hear you.
Okay, you can start, please.
The title of my presentation is Upper Bounds of the Third Order Henkel Determinants for the class of star-like function of order alpha. In abstract, in this paper, we consider the classes of star-like function of order alpha analytic in the one-hit disk and normalized by f of 0 equals 0 and f prime of 0 equal 1. We study the third order Henkel determinants 8 dr of 1 for these classes and derive an upper bounds for absolute value of 8 dr of 1. Our results extend and complement recent contributions by Braz, Cătaș, and Cotârlă concerning subclasses of analytic function associated with the exponential function. Table of contents, introduction, preliminary results, main results, conclusion, and original contributions. Introduction, definition and context. Definition 1, we consider the classes A in the next relation 1. We denote by as the subclasses of univalent function in A. The Bieber-Bach conjecture stimulated the study of special subclasses of S. Definition 2, an important subclasses star-likes. In the next relation 2, definition 3, subordination. We say that equation where W is a Schwarz function. Maminda introduces the general classes star-likes and convex, where Rep of Z is greater than 0 and phi of 0 equals 1. For inequations, in the next relation 5,
we obtain the Javanovsky classes, and for relation, we obtain the classes star-like alpha. For relation, the Henkel determinants are defined by in the next relation act, in particular, Henkel determinant act 3 of 1 object to determine the upper bounds determinant Henkel act 3 of 1 for the classes star-like. Preliminary result for phi f belongs to star-like, you have the representation equation where P belongs to classes P. Definition for the function for the Kara-Teodori classes in the next relation. The coefficients Cn of P are controllable and play a crucial role in estimating the coefficients of f and the Henkel determinants. Proposition 1, Kara-Teodori, for P belongs to classes P, we have the fundamental proprietary in the next relation. This result is essential for the subsequent estimation. Preliminary result, lemma 1, Kara-Teodori, for P belongs to classes P in the next relation. Lemma 2, lemma 2, Libera, Jolte, Livston in the next relation. Lemma 3, Libera, Joltevisk in the next relation. My result, definition 5 on theorem 1. Definition of function f belongs to S is said to belong to the classes of star-like function of order alpha 0 less than or equal to alpha less than 1 if it satisfies the condition in the next relation. For alpha equals 0, the family star-like 0 coincides with the classical class of star-like function. Theorem 1, if the function f belong star-like alpha where relation, then you have equations in the next equations. Proof, theorem 1, since f belongs to star-like alpha, be the definition of subordination, there exists a Schwarz function double wz with w0 equals 0 and absolute value wz less than 1, such that in the next relation, on the one hand, you have the standard expansions in the next equation. On the other hand, denoting equation, you can write in the next relation. From the previous relation, you obtain in the next relation. Be comparing the coefficients you obtain in the next relation. T4 in the next relation. Thus, theorem 1 is fluffy provide. Theorem 2, if the function f belong to a star like alpha, where in the next relation, then you have in the next equation. Proof theorem 2 from the coefficient relation obtained earlier, you have in the next equations. Therefore, equation applying lemma 3 in result in the next equation with with absolute value x less than or equal to 1, absolute value z less than or equal to 1. And using the triangular inequality, we obtain equations. Reapplying lemma 3, we have equations using the parameterizations in the next equations. With relation, we obtain after simplification in the next inequations since since absolute value C1, C2, C3 less than or equal to 2, it flowers immediately dead in the next equations. Thus, theorem 2 is fully provided.
I'm sorry to interrupt, but could you please hurry up?
Okay. Theorem 3 in the function f be along the star-likes where relation, then you have inequations. Proof theorem 3. The proof of this theorem is as follows. My result theorem 4. If the function f belongs star-likes where relation, then the third order Hankel determinant satisfies in the next relation, in particular since 0 less than or equal to 1 minus alpha less than or equal to 1. We have the numerical bounds in the next equations. Proof. The proof of this theorem is as follows. A conclusion and original contribution. In this work, we obtain upper bounds for the third order Hankel determinants, 3 of 1 in the classes of star-like function of order alpha, star-like alpha. The strategy followed was identical to that is in the article by Braskatash and Coturle, writing the expansion of relation in terms of the coefficients a n. Uplink subordination relation on the liberal Roltekevich parameterization for C2, C3 using no inequality for the coefficients of function in classes P, deriving bounds for the functionals in the relation and then for A3 of 1. The original contribution consists of the fact that we apply this method to the fundamental classes star like alpha, for which the literature did not previously provide an explicit upper bounds for ATDR of 1. We obtain a clear and numerical expression in the next equation and in a particular relation. The bibliography used is the flowing. Thank you for your attention.
Okay, thank you very much. Are there any questions? No? Okay, thank you.
Thank you.
The next paper is presented by Khalifa Bumzouh, Andane Azouzi, Abdeljalil Naouchi, the convergence of the JN relaxed algorithm for convection diffusion Cauchy problems.
Hello, you hear me?
Yes, we can hear
you. You see my presentation? Okay, I will start. So, good afternoon, everyone. My name is Khalifa Bumzouh from Morocco. It's a pleasure to present our work today in this conference. So I will talk about the convergence of GN relaxed algorithm for convection diffusion Cauchy problems. This is joint work with Professor Abdeljalil Nashawi and Professor Adnan Azouzi. So my presentation is organized into 5 parts. Firstly, I will start with introduce the problem we are solving. Then I will explain the GN algorithm. In the third part and fourth part, I will present our studying convergence analysis and acceleration of this convergence. Finally, conclusion. So, inverse Cauchy problem arise in many contexts where boundary measurements are incomplete. Typically, part of the boundary is inaccessible, but we want to recover the missing information there. For example, problems associated with convection diffusion equation. So these equations model transfer diffusion phenomena in various fields. They arise in physical processes such as heat transfer and fluid mechanics. So the inverse Cauchy problems of this equation are all posed, requiring advanced technique to ensure stability and convergence. So because that we use the algorithm GN relaxed for solving the inverse Cauchy problem. So we are interested to studying considering the convection diffusion equation defined as like that. We have R positive is diffusion equation and gamma is the convection velocity field. So we considering this rectangle domain, we have directly condition boundaries in sigma 1 and sigma 3, and we have both condition in Newman and directly data on the right boundary gamma m. Our objective is to constructing the solution everywhere, especially in gamma U, especially in the left boundary gamma U, where we have no data. So also we are objective is analyzing the convergence of the GN-relaxed algorithm theoretically and studying the acceleration of this convergence. So let me now explain the structure of the GN-relaxed algorithm. The idea is to alternate between two problems. An old iteration problem with directly data on one side of the boundary and even iteration problem with Newman data on the same side. At every iteration, the algorithm updates to estimated of the missing boundary data to n using accelerated parameter using our relaxation parameter theta. So in the step 1, we have initialization. We begin with initialization the gas to 0. On gamma U, this gas does not need to be accurated because the algorithm converges independently of it. We solve a first well-posed problem. And the second step 2, we have for odd iteration, we solve a well-posed boundary value problem with directly data on sigma 1 and sigma 3. On directly data on sigma m and Newman data on sigma u. Taken from the previous even iteration, this problem is well posed and produced to updated solution. And step 3, even iteration with relaxation to solving another well-posed problem, now imposing Newman data in gamma m and directly data in gamma u given by the relaxed updated. And for the step 4, we repeated the odd and even iteration in initial convergence. So the main result of this study is summarizing in the following theorem. Consider the convection diffusion equation defined in the equation 2 iterate 4. So we have the sequence UN converge to the solution the Cauchy problem in equation 1 independently of the initial value to 0 if we have for all theta is between 0 and theta starts, where the theta starts equal this formula. So for analyzation, studying the convergence of this algorithm, set we let Wn equal U minus Un. Then from the applied Gn relaxed algorithm for the sequence Wn is given as the following. Step 1 is initialization problem, and step 2 solve odd problems, and step 3 solve even problems. So we need for proving the theorem 1, we need some lemma about the general solution. The general solution the sequence the general solution for even problem is explained as the formula, and the general solution for the odd problem is given as this formula. So the idea of proof, we assume that the separation solution that we use Wn equal xn yn. So we're using the technique of separation of variable obtained into the convection diffusion equation give to independent ordinary differential equation defined like that. So we have we have four equation, ordinary differential equation. On second order, we using the technique to solving of this ordinary differential equation. So we obtained for general solution of the y problem in the 12, we get this formula. We using the condition we obtained the y to n equal this formula. So the general solution of the x problem in the in 12 we get like that, and using another the condition we obtained the expression of the x to n. So by combining the x to n and the y to n, we obtain the general solution for w to n. We use the same technique for w to n plus 1. So we need also this lemma considering the w to n and w to n plus 1 in the problem 6 and 7, 8. Then the coefficient, we have the coefficient a to n and e to n plus 1 in the equation 10 and 11 are given dependent of the E0 as the where the A0 equal this formula. So for that, we using n equals 0, we applied the boundary condition of the problem 6. Problem 6, we have W0 equal U minus 20. So we obtained the A0 equal this formula. So then we using the boundary condition of the problem 7, we have also obtained to E0 equal H beta M E0. So for n equal 1, we applied the boundary condition of the problem 9 and 8 respectively. So from this problem defined by W2 equal theta W1 plus 1 minus theta W0. So when you applied, we obtained to E0 dependent to A0. So for the solution of A to n solving this the recurrence given like that, we obtain to E to n dependent to E0, and using the same technique we obtained titled E to n plus 1 dependent of the E0. So we need also this lemma if we the sequence W to n is defined like W to n.
Excuse me, please hurry up with your presentation.
Okay.
Thank you.
Okay, we have this. We need also this lemma for proving the theorem 1. So for that, we have initialization. Let's consider the norm W to n equal defined like that. By Cauchy-Schwarz inequality, we have this formula. By Parseval identity, we obtained this, and we can define the norm of W to n in L to equal defined like that. So norm of we interesting to proving this theorem 1, we using like that. We have to this formula for that. The condition convergent condition, if we have theta h beta n plus 1 minus theta is between 1 and minus 1. So finally, we obtained theta is between 0 and theta starts defined like that. So this amply the sequence U converge to the solution, exact solution U. If we have theta is between 0 and theta start, guarantee the convergence of this algorithm. For the acceleration of the convergence, we have this theorem considering the convergence diffusion convection diffusion problem defined in the equation 2 and 3 and 4. So we can just say the convergence of the algorithm G-Relax is faster than the KMF algorithm if we have theta is between 1 and theta b. So this is the proof of this theorem. So, as a conclusion, we can conclude the GN-RELAX algorithm ensure fast and stable conversion for all posed Cauchy problem. And theoretical result highlights its important role to data is improving efficiently. Thank you for your attention.
Okay, thank you. Are there any questions? Okay, thank you again.
Thank you.
Thank you very much. Our next and final talk will be given by Marwa Ahmed Bubakar, which he will give a talk on a hybrid differential framework for horizontal and horizontal vertical transmissions.
Yes, I'm here. Thank you. Hello everyone, welcome to my presentation. The title of my work is Hybrid Transmission Framework of Horizontal and Horizontal Vertical Transmission. First, I will give an introduction to prove the motivation of my work. Next, I will cover the primary concepts with include the key mathematical definition and necessary to understand the model. After, I will present the mathematical model explained by equation, and finally conclusion and numerical simulation and some references. In this part, I introduce some important definition of fractional derivative that we use in our model. Fractional derivative allow to include memory effects in a biology system, with is very important when modeling long-term size. We start with the Caputo-Fabrizio derivative we use in exponential kernel. Here I present the classical Caputo on the Riemann-Wheel. The Caputo derivative is very common in epidemiology because it works with the standard initial condition. The Riemann-Wheel derivative is more general but more difficult to apply in this size modeling. This slide introduces the Atangana-Baliano derivative. It uses the metal-Leffler kernel with give a realistic mix of a fast and slow memory decline. This makes it suitable for modeling the size that persisted for the longer time, like HEL. I show the fractal fractional derivative. This derivative introduces a new parameter called beta, which represents the fractal natural of time. This means that time does not always progress uniformly in a real biological system. Here we present the fractional integral. This integral are important for proving existence of a solution and for building numerical method. The fractal dimension beta influences how memory accumulates over time. Now we move to epidemic model in the first phase. In the first, I will explain this model. An initial operation of the size in the population, it's not always the case that can be transmitted both horizontal and vertical. For interesting, when the COVID-19 first emerged, it was initially believed that the size could only transmit horizontal and horizontally. However, as the epidemic progressed, it was discovered that vertical transmission was also possible. In this part, we address a scenario in which vertical transmission began after an initial period of horizontal transmission. We developed a mathematical model using the framework of piecewise differential equation. To achieve this, we adopt a model proposed by Yusuf and the colleague, which was original designed to monitor both vertical and horizontal transmission of HIV function at a time. In the first phase, from time 0 to T0, the decisive in transmission is only horizontal. There are three populations: susceptible adults, infected adults, and newborn child. After time T0, vertical transmission began. We added a new equation for newborn that are infected at birth. The piecewise structure allows use to describe the change in transmission dynamics. To analyze the system mathematically, we rewrite the model in a vector from this make to study existence and uniqueness and numerical method. This theorem gives the condition under which our model has an unique solution. The function need to be mutable and in the time continuous in the state variable and bound by a null function. Here we show that the solution does not blow up in finite time. This means the model is well posted and valid for long time epidemiological studies. Now I will present. I describe the numerical schema used to solve the Caputo-Fabrizio model. The method accounted for the non-local structure of the derivative. We compute the solution spatially of the two phases of the two systems, 0 at T0 and T0 T final. This is some graphics for Fabrizio derivative for infected and for different alpha. That's it. Next, I will describe plots show numerical result. We observe someone dynamic and a clear memory effect to do the fraction derivative. This is for Caputo. And finally, I will present the numerical simulation of the Caputo. Because the kernel is a power law, the schema require more refined approximation. This method will be used to compare the Caputo and the Caputo-Fabrizio. Finally, I will give a conclusion. In the model that consider horizontal and vertical transmission, HIV transmission, an increase in the adults, an increase in susceptible. The population of susceptible adults allowed there are model literature, and the study consider this scenario using a new concept called piecewise differential equation to prove the dynamic of this epidemic. This is some references. And thank you for your attention.
Okay, thank you. Are there any questions? Okay, so then congratulations to everyone for your presentations. And
Thank you.
the session is now over. Have a nice day.
Thank you so much. Have a nice day.
Goodbye.
Goodbye. See you later.
Bye bye.